seesaw. Okay. I'm gonna do the seesaw problem again, but I'm gonna show you something different this time because this is important. Okay. So I've got the seesaw. Okay, and I've got my person here, and I've got my person here, right? Okay. Free body diagram. To draw a free body diagram of these torque problems, you do it very simply. All you do is you draw a line for the bar. If it's a bar, you draw a line. Okay? Let's talk about the forces. What are my forces that are on the seesaw? What are my forces on the seesaw? From what? So both of the people. I have a force. I'm going to call this F2 for this guy. I'm going to call this one F1. Are these all my forces? How do I know that these are not all my forces? But how do you? Yes, but right. If I look at this as it exists, this is telling me that the seesaw is going to fall straight down. I have to have something pushing it straight up. The normal force, where's the normal force coming from? The center, the pivot point. So there's a normal force here. Okay? And remember we said this was like L1. Here's my F1. Here's my L1. Here's my L2. Right? Here's my force 2. So I've got a force 2, a force 1, and a normal force. A force coming up from the pivot point. Does that make sense? Okay. So if I do this, and let's say F1 equals 10 newtons, F2 equals 10 newtons, and let's say L1 equals 5 meters and L2 equals 5 meters. Okay? Now, remember, F1, the force 1, is trying to twist the seesaw this way, creating torque 1. And force 2 is trying to twist the seesaw this way, creating torque 2, right? And it's balanced when the torques are equal and opposite, right? Okay. I'm going to move this over to here for a minute. All right. So here's the thing. A couple of things. Let's look at, because we have these forces and this free body diagram, let's do the sum of the forces in the y direction. Are there any x direction forces? No. So what are my forces that I can sum in the y direction? F2 plus F1 plus Fn, right? If the seesaw is not moving vertically up and down, what are the sum of the forces equal to? 0. My net force is 0. My net force is 0. And let's do this. Do I know the value of Fn yet? No, I don't. So let's solve for it. So F2 is, what's F2? Is it 10 or is it negative 10? What direction is it going? Negative. So it's negative 10 newtons plus what's F1? Negative 10 newtons plus Fn equals 0. Therefore, Fn must equal what? 20 newtons. Positive. Does positive make sense? Okay. Clear? Okay. Now, yesterday, we talked about the sum of the torques, right? And I'm going to call this point A, point B, and point C. Yesterday, we did the sum of the torques around point B, right? And we said there were some torques. What were the torques that we were summing up? What were the torques that we had? But on this problem, what would be the torques on this problem? What would be the torques that we're going to sum up? Torque 1 and torque 2, right? Okay. And we said yesterday those two are balanced, so they should be equal to 0, right?
Right.
Okay. There's actually a third torque that we're not talking about. Where's the third torque coming from? Fn. So there's a torque from my normal force. There's a torque from the normal force. All three of those equal 0. Now you're saying, but Mr. A, that wasn't there yesterday. Let's explain why. For torque 1, let's break it down. Torque 1 is equal to what times what? Force 1 times. Torque equals what? Length 1, right? Okay, force 1 times length 1. Plus what's torque 2? Force 2 times length 2. Now, if I looked at Fn, what are the lengths? The lengths are from what to what? From where to where? No, the lengths are from, in the torque, the length that I use in the equation is from where to where? From the pivot point to the force location, right? The lengths are from the pivot point. When I look at the lengths in this equation, these lengths are from the pivot point to the location where the force is acting. Does that make sense? So in this case, they're both. In this case, L1 is what? 5 meters. So I'm going to say, okay. So hold on. I'm going to say this is plus Fn times LFn. Okay. So F1 is what? 10? F1, what is it? Negative 10 newtons. F1 is 10 newtons, but it's negative 10 newtons. What's L1? What it? It's right at the pivot point it's right of the point around which we're summing the torques. It's right of B. Force 1 is to the right of B, therefore it is positive, right? So it's going to be times 5 meters. Plus, what's the value of F2? Negative 10 newtons. Times, what's the value of L2? Negative 5. Right? Because it's to the left of the point that we are summing the torques around. Cannon, are you with me?
Yes.
Plus, Fn Fn we kind of do know actually, right? It's 20 newtons. Is it positive or negative? 20 newtons. Times what's the distance between what's the distance between the pivot point, what's the distance between the point around which we are summing the torques, which is what? Point what? B. What's the distance between B and the normal force? It's 0.
How do we know that?
Because we're summing the torques around point B, which is the pivot point. The pivot point, force N, is actually coming from the pivot point. You follow me? So if the force is actually at that point, then the distance between the force and that point is 0. That's why it didn't exist. This torque Fn goes to 0. That's why when we did it the first time, it didn't exist.
So when would it not equal 0?
Okay, I'm going to do an example in a minute. Okay, so now let's prove this out. So we assume that the sum is supposed to equal 0. Let's make sure it equals 0. What's negative 10 times 5? Negative 50, and what's the unit of torque? Beautiful. What's negative 10 times negative 5? Positive 50 Newton meters. What's 20 times 0? 0. Does negative 50 plus 50 equal 0? Yes. Check. Right? We're good? Okay. Now, here's the magic, and I'm going to show you the example. We took the sum of the torques around the center point, because that's the obvious. Well, hey, it's pivoting on the pivot, right? That's your experience. The interesting thing is that if I were to do this equation around point A or point C or any point along this bar, the torque summation would always equal 0 if it's balanced. Let me explain what I mean by that. Let me grab it. Okay. Here's I need a volunteer.
I'll be your volunteer.
There will be blood. There will be blood.
I actually did that one time.
He's a driller, he's actually drilling underneath. It's somewhat physics work. Okay.
No, if you connect a bunch of straws to the vacuum machine, and you can put your drink in there, but push it all the way back to where it's gone, and then you can get really far away and just drink it, and just go through it.
Alright. Here's what I want you to do. Can't. Okay, actually need another volunteer.
Turgeon.
Here's another volunteer. Okay, come over here. Okay, Tara, I want you to be the fulcrum. I want you to put your fingers right there like that. Ken, I want you to put your fingers like this. Okay, now. Ken, I want you to pull down like you're sitting on the seesaw. Okay, and I'm going to pull down like I said. And your job is to do that.
Strong.
Don't overdo it, okay? So, now you feel what kind of force? Not force, right? But if I were to let go, and you want to balance it, what's going to happen? You have to actually create a torque. So let me think. Actually, you let go for 1 second, okay? Now, Ken and I are here. Now, Ken, without this fulcrum, okay? If I were to pull down, what do you feel over there? A torque. Oh, wait a minute. There's a torque there. Even though it doesn't look like there's a torque, there's actually a torque there because I'm doing it. Now, Kara-Jane, put your. Now I'm trying to balance that. You still feel that potential torque, right? But you're going to be pushing down. Same thing on this side. There's a torque on my side. And if I let go, she's going to feel a torque, right? So thank you very much. There are torques. There's a torque at every point. Okay? It really depends on who's better. This point, the pivot point where Kara-Jane was is creating a torque around this point, right? No, but it doesn't move, but there's still a torque. Because if it wasn't there,
Yes. Make them feel it.
okay, here.
Once you feel it.
Okay. Feel it right here. Put your finger right there, okay? Don't you feel the torque? The twist? Because my force is pushing it. Right? You have to actually pull it down. There's a torque. There's actually a twist. And you feel like, well, it's not moving, but it actually, there's actually a torque because you're trying to do this. Because it's a force at a length. It's all perspective, right? You're pulling down at this length, or this is pulling up at that length. But if it was a bigger force, then you'd feel it. But right now, you don't feel it because it's balanced. Does that make sense?
Yes.
Okay. So, oh, my back. This is not OSHA compliant. Okay. OSHA work. This is like a work safety. This is definitely not ergonomic. Huh? Yeah. OSHA. Okay. All right. Quiet. What's going on here? What is happening? Okay. So let's do the whole thing. Shh. Let's do the whole thing again, but we're gonna do the torques, girls, around a different point. Rather than B, we're gonna do it around A. Okay? So I'm gonna do the sum of the torques around A. What are my torques that are generated around A? What are the torques that I'm gonna sum up around A? Wait.
Would it be the same?
Wait. Shh. Why would it not be? Why would it be the same? You're right, but why would it be the same?
They're all going around it.
They're all there. One's going to be 0, but it might be a different one this time. The torques are always going to be. It's always the same ones. They're always going to be there. So when I sum the torques, it's still torque of 1 plus torque of 2 plus torque of Fn, right? And they should, if it's balanced, equal what? 0. Now let's break this down. So torque 1 is, let's look at this. Torque 1 is my force 1, right? Times what's the length from force 1 to the new pivot point A?
10 meters.
Well, let's do it in variables. Here's force 1. Here's force 1. Here's point A. How far is force 1 from point A?
2 times L2.
It's L1 plus L2, isn't it? Right? Do you guys see that?
Yes.
It's at full distance. Torque 2 is what? F2 times what's the distance between F2 and now point A? 0. Does everyone see that?
Yes.
Okay. Now, Fn, the torque of Fn is my Fn times what's the length, the distance between Fn and A?
L2.
L2. Do you guys see that? Okay, I'm using L1 and L2 because just because I said it was 5 meters and 5 meters, it may not always be that way, right? You guys follow me?
Wait, can you explain the second torque?
Which one? This one?
Yeah.
Okay. So we're in this new equation, we're summing the torques around point A. So we're looking at and again we'd say torque is equal to force times the length perpendicular to the force, and that length is between the force and the point around which you are summing the torques. In this scenario, we're looking at point A. We're summing the torques around point A. So Fn is only L2 away from A. F1 is L1 plus F2 away from A. F2, how far is F2 horizontally from A? 0.
Okay, so you're doing F2, not doing.
Torque 2 is from F2. I stated that torque 2 is from F2, right?
So
So
it's like the Fn in the first one, right?
right. It's like it, but don't just memorize it like it. Just it's coming out the same way. But think about the idea is we're always measuring, the L is always a distance from the force to the point around which we are measuring the torques. And I say pivot point, but you have to be careful. This is the physical pivot point. B is the physical pivot point for the seesaw. But when I sum my torques, that pivot point is the point around which I mathematically sum the torques, which may or may not be the physical pivot point. Because I can sum those torques around any point on this bar, and it'll always come out to be 0 if my bar is not moving. Does that make sense?
Yeah.
Okay. And I'm proving that here, and we're going to finish the proof. So if it's balanced, my torque should be balanced, so it should be 0. So let's put the numbers in. What's F1? Negative 10 newtons. What's L1 plus L2? 10 meters. Is it negative or positive? Why is it positive? To the right of now A. Does that make sense?
Yes.
Okay, so it's 10 meters.
How come?
Hold on. Go ahead, yeah.
How come F1 wouldn't be positive?
Yeah, if one's going what
Oh,
direction?
that's right.
Down. So F2 times 0 is 0. And Fn, what's Fn? Do we know the value for Fn?
20.
Is it up or is it positive or negative? Because it's pointing up, so it's positive. So it's 20 newtons times what's L2? What's the distance between the normal force and point A? 5 meters. Is it positive or negative?
No, positive.
It's positive because it's to the right of, look, of the new point. Yes, yes. So 5 meters, right? So let's calculate it out. So what's negative 10 newtons times 10 meters? Negative 100 newton meters plus 0 plus what's 20 newtons times 5 meters? I'm sorry? Yeah, it's 100 newton meters. And therefore, it does in fact still equal 0. So I've proven to you that no matter what point you take it around, it will always still equal 0.
So you're proving that it's 0.
What I'm proving is that you can take the sum of the torques around any point on that seesaw, and as long as the seesaw is balanced and not moving, then the sum of the torques will always be 0, no matter what point you calculate the torques around. Does that make sense? I'm trying to separate the physical what you think is the physical balance point or pivot point to what we're doing mathematically, and we're summing it around. Okay? All right. Everyone clear on that? Good. Okay. Sorry. I'm trying to figure out how far we go between now and 10. So this is going to be
As far as you think we should go.
okay. Well, this is as far as I want you to be able to go. Now, for a test question, okay, I'm not done. She was like, okay, let's go.
Not 10 minutes. Or like
Tara
45,
Jane's
not
like,
10.
lunch.
Yeah. It's really just such
She's
I
gonna
know.
sprint over there.
But the lines are gone in like 10 minutes. By the time I get there, there's never usually a line. And there's never food. Okay. Okay.
If you don't know,
Okay. So for a test question for torque, guys, for a test question, Hannah, for torque, okay, I could give you something like this, all right, where it is something like this or like the door from yesterday, and I could ask you to figure out the different forces that are there, okay? When I think about the door, all right, so I could ask you, like I could give you like different lengths. There's 5 variables. There's F1, L1, L2, F2, Fn, L2. So it's 1, 2, 3, 4, 5 different variables, right? I could give you any 4 of them and have you find the 5th one, right? You're going to have to probably go through the sum of the forces and the torque to get to where you need to go. Okay? Does that make sense? So, what an example might be, may I erase this? Yes, you have a question? Hmm?
Is this going on test Monday?
Mm-hmm.
So is it force through torque?
Force through torque. So that's force, pulleys. It's a lot.
It was like the last quiz.
Last test.
Or,
We had
the worksheet that we had.
That's the last test.
what?
We had to do that worksheet.
Yeah, we had 2 tests.
What about
So it's the last two tests for the grade.
This will be the last exam in their grade book.
And we have like group
We will do another assessment before the end of the year. Yes, sir.
Are we gonna be able to have no card on this test?
Yes, always get a no card.
Really?
Always. Okay, may I erase this?
No.
Wait, how big does the note card can be?
3 by 5. 3 inches by 5 inches.
Only 3 by 5?
Only 3 by 5. Okay. So, here's the door example from yesterday. Okay, here's the door example from yesterday. Again, the same rule applies. When we did the free body diagram, remember we had the door handle, the pushing force, and we had the spring force, right?
Yes.
And we drew the free body diagram, right? Okay. So here's the thing. So here's my push force. Here's my spring force. Are those the only 2 forces I have on the door? Where's the other?
It's the other way.
Oh, I'm sorry. I screwed that up. Okay. Where's that force? At the hinge. There's another force at the hinge. Call it force hinge. Do I know what direction that force is going? I don't. But I can have you solve for it.
You sure can.
Right? And if you figured out this force and this force, So how would you solve that? So I'd say, okay, let's say you did your torques. I gave you this force and that length, right? Huh? Well, let's do it. Let's say this is 10 newtons and this is 30 newtons. How would you determine Fn or Fh? Let's say the door is balanced right now. Sum of the what? In the y equals
Or technically,
Fp plus Fs plus Fh, right? And what's the value of Fp? Positive 10 newtons. What's the value of Fs? Negative 30 newtons. What's the value of Fh? So Fh, if it's balanced, the sum of the forces equals what?
0,
Okay, so now Fh is equal to what?
0.
No. 10 plus negative 30 is negative 20, so fling it over there, and it's 20 newtons. So Fh is pushing, which direction is Fh going? Up.
Well,
I'm calling it the hinge, the force at the hinge.
So does FH change depending on which way you're pushing from?
Yeah, it would, wouldn't it? No, I'm serious. I know, I'm sorry. Yeah. Yeah. No, I'm serious though, right? So let's look at this.
I'm surprised you didn't get candy.
Huh?
I'm surprised you didn't get candy.
Okay. Let's assume that my FP was now this direction. So that's going to be a negative 10. Oops. Yeah, so it's going to be negative 10, right? So it's still going to be going the same direction. So it's going to be 40, right? But I'd have to really change this guy. I'd have to really change because I have to change the spring direction, go the other direction for the spring. I have to go this direction for the spring in order for it to change directions. Oh my goodness. Okay. Any questions on that?
That would explain why pushing a door requires more force than just like letting it go.
Because why?
Because you're working against the screen.
Right.
And you're also
But it's also, but more importantly, it tells you why it's easier to push the door on the far away from the hinge than from closer to the hinge, right? All right. Are there any other questions before the exam? Okay, tomorrow be prepared to work. Tomorrow be prepared to work.